In today's lecture, we will discuss about um, the Cauchy-Riemann equations and the stress function, which was created by Irwin. And then, if time permits, we'll go in the plastic zone size, and we will continue from the expression of stress intensity factor to a constraint parameter T stress. In this continuation, we will proceed. So before we go to Cauchy-Riemann equation and we go to the stress intensity factor expression, we need to understand a few basic things. So if a function, a stress function, is described by the symbol phi, then stresses, if the stresses are described in this format, so del 2 phi by del y squared and sigma yy is equal to del 2 phi by del x squared and sigma xy is equal to del 2 phi by del x del y. Then whatever is the value of function phi, it satisfies two of the important conditions which are required for the stress and strain to hold good for a material point. So first condition is stress equilibrium. So first condition is stress equilibrium, and the second one is compatibility, strain compatibility. So not without going into detail, I'll tell you what it is, compatibility equation, and both of them are described in a way. So stress equilibrium is already satisfied if the stresses are described by this relationship. So now let us examine the stress equilibrium, which is very basic, and I will do it as faster as possible. So imagine that on an object you have a point. So on an object, basically there are infinite number of material points you can have. So let us take one point, and this point, if I exaggerate in my view so that it looks like this cuboid, and then I will describe the things which are happening on the cuboid. So let us say that this is the origin and this is, say, x direction, this is y direction, and that is z direction. And now let me look at this cuboid in two dimension in xy plane. So if I look at this in xy plane, then for equilibrium to maintain, what I need to do is that there should be no translation and no rotation on this cuboid. So for that I need to do forces in all direction equals to 0. So let us say that the stress which is working in this direction is sigma xx, and intuitively I can say that the stress in this direction should also be sigma xx. But let us say that it is not the case. This is how we proceed in mathematics, by saying that it is not the case and then we prove that. Then if it is not the case, then things are not good. So let us say that the rate of change of the stress along x direction can be given by this, which is what it is. And therefore the stress on this side, so let me name this is A, B, C and D. So the stress on the face BC is going to be sigma xx plus rate of change of the stress along x direction multiplied by the distance, which is delta x. Okay. So for simplicity, I'll do it in only in one direction, and the same thing can be repeated in y and z direction, and you will see that it will be similar. The derivation will be similar. So apart from sigma xx, the stress which is working in x direction is also sigma yx and sigma zx. So in two dimension, I will not consider that. I will only consider sigma yx, and there will be another stress on the face AB, which will be sigma yx plus rate of change of sigma yx in this direction. So that dimension is delta y. So that will be multiplied with delta y. Okay. So in two dimension, if I do the summation of forces in x equals to 0, then I need to find out the forces which are there in the x direction. So the net force will be sigma xx plus del of sigma xx del x multiplied by del x. This is a stress, so I need to multiply this stress with the area to get the force, and the area is the area of the face BC, and that area is will be something like that. So that area is going to be this dimension into this dimension. The height of that is delta y, and there will be delta z. So because we are doing it in two dimension, so there is no delta z, so it will be delta y, and then I will have sigma xx into the same area, which will be delta y, and then I have the shear stress, which will be, so I will have sigma yx plus del of sigma yx del y multiplied by delta y, and this is again the stress, and this stress is multiplied by this. So if this is the cube, the square, then the shear stress is acting on this plane, and this plane is this dimension, which is delta z, which we don't have, into this dimension, which is delta x. Okay, so this will be multiplied with delta x. So here I will have delta x minus I will have sigma yx delta x, and this must be equal to 0. I'm ignoring the z direction, but if I don't ignore it, then if I would have done it in three dimension, then I can consider delta z here, delta z here, delta z here, delta z here, and I will have another force which will be sigma zx plus del of sigma zx del z multiplied by delta z delta x delta y minus sigma zx delta z delta x delta y. Okay, and this would have been equal to 0. So you see that this multiplied by this will be cancelling with this. Okay, so these terms will get cancelled, this and this will get cancelled, and this will get cancelled. So I will have del sigma xx by del x plus del sigma yx by del y plus del sigma zx by del z will be equal to 0. And this I am getting by doing summation of forces in x direction equals to 0. Similarly, I will do summation of forces in y direction equals to 0. And following the same pattern, you can yourself write that it will be sigma y by del y plus del sigma x y by del x plus del sigma zy by del z will be equal to 0. And similarly, there will be one more equation, and these set of equations are stress equilibrium condition. And this equation is already satisfied for whatever value of phi when you use this relationship of stresses with the stress function. So one condition is already satisfied when we have this. The second one is called strain compatibility condition. And this condition we will not derive because that is complicated and out of scope of this course. Compatibility equation. And this equation can simply be written as del 4 phi by del x 4 plus 2 del 4 phi by del x square del y square plus del 4 phi by del y square equals to 0, and it is also written as nabla square phi equals 0. And this is called biharmonic function. If a function follows this, it is called biharmonic function. So what does this equation in physicality mean? That I will tell without deriving this. So imagine that you have an object made up of, say, trusses. So A, B, and C are three beams which are connecting each other. And after deformation, A, B deforms to A dash, B dash, and AC deforms to A dash, C dash, and this deforms to B dash, C dash. So you see that if you allow the three beams to deform freely, following the other things, the stress equilibrium and all, then it may so happen that they overlap on each other or they do not meet. So there are either gaps or intersections. So the condition, the strain compatibility condition, imposes this that these three nodes should be connected if there is a deformation. This is what it in simpler language. This is what it means.